So the first talk is by Tim Buckner. Okay, it's the first talk of the oral session. So after the talk, we'll have like 5 minutes of Q&A, maybe a bit more. Okay, cool.
Okay, welcome and good morning, everyone. My name is Tim Büchner, and I'm going to present our this year's CVPR work, EIFER, Electromyography Informed Facial Expression Reconstruction for Physiological-Based Synthesis and Analysis. And the main research goal we are trying to solve is here, we want to understand the nonlinear bidirectional correspondence between facial expressions and the underlying activation of muscles. And our goal is twofold. A, we want to synthesize more natural expressions based on these EMG muscle data, but also we want to go to a more camera-based only muscle analysis. And of course, we are not the first one to do this research. There's many work, and we could go back even further in timeline. And what we are interested in is more the anatomical side of this. And I think many of you know the facial action coding system established by Professor Eggman and Friesen. And we will take a different, more data-driven approach to that. And especially, we do not believe in the hypothesis of like a single muscle resolves in a single facial movement. And where we are coming from is basically from a medical perspective. I will show you 2 videos, and you will see not everything is like in a normal face. On the left, you can see a patient which has a synkinetic effect. He tries to raise his eyebrows, but on the same time, he automatically moves the side of his mouth. This is completely involuntary. And on the other side, we have like full facial palsy for a patient. She tries to smile, and only one side of the face is working at all. So all these hypotheses we have for the face from a medical perspective are a bit broken by different kind of diseases. And this is where we're coming from. We are a research cooperation between a computer vision group in Jena under Professor Denzler, where I'm part of, and the ENT department under Professor Koninas Lichios. So we have a lot of medical expertise and knowledge and can also acquire healthy probands and patients in this manner. We have experts for psychology, facial paralysis, and electromyography data. And to go back to the big question, like to understand the nonlinear bidirectional correspondence, we are data scientists in the end. We have to capture data. So what we are doing is we want to capture muscle activity and facial movements simultaneously. And that's what we did. So basically here you can see me in a new recording where we have like synchronized the video and the SEMG data. And I, in this case, mimic the 6 basis emotions defined by Eggman. And we do this for way more movements. We do this dynamically. We capture everything. And I think you can already see a bit the issue in this kind of capture. The thing we want to actually visually capture, the facial expressions, are actually covered by the electrodes. So we are like an ill-posed problem. And if we just use one of these existing pipelines, for example here, this is based on Smirk, it somewhat tries to reconstruct whatever's happening there, but nothing really works. It's okayish, but like all the assumptions they do about like that the face is not occluded because to estimate landmarks or anything doesn't work anymore. And also another thing is the reconstruction is not suitable for any downstream task. So we cannot do like facial expression recognition anymore or other stuff. So coming back to the problem is what we basically want to do is like we want to isolate the expression to actually like have the ground truth for or like to describe the face using here a 3D model, in this case flame. And we have the corresponding ground of EMG. So the task is now just isolate expressions, and then we can just learn this correspondence. Easier said than done. And what I now propose is our method EIFER. What it basically does, we get one of these occluded input images. We are able to reconstruct the underlying facial geometry using flame, and at the same time reconstruct the true or like the face without these occlusions. And then we are able to do analysis. So we basically learn the correspondence from the expressions to the muscle activity, but vice versa. If we would just look at the muscle EMG data, we can also synthesize new expressions. And this is what we are solved in this problem. And the basic pipeline really broken down is you get an occluded image, then we have the EIFER processing, which does like the encoding of the face, as we also seen in the previous keynote talk. For the reconstruction of the face, we're using a neural generator, so we do not have a real appearance model, but we use an unpaired reference image we have of the same person during training to train like a generative adversarial network to do the appearance modeling in our case. And by this adversarial manner and the cyclic structure we're using, we are able to reconstruct the face in a somewhat realistic manner. And if you're really interested in the whole idea of what we are doing in the background, you can come to the poster and I actually talk about the whole pipeline, the constructed things we are doing to constrain the model in itself, because under the occlusion, we cannot confirm that we have like a perfect pixel or like pixel perfect ground truth version of the face, because the person doesn't do the same expressions twice the same. We have different kind of lighting conditions. People do the same expression in a different speed. So there are a lot of problems, and this way we can avoid it without having that. And lastly, if you take a look at this, we can now solve 3 basic tasks. A, we can isolate the expressions based on this video, so we can use this later for this mapping. But also, as you have seen in the other images, the reconstructed faces look quite naturalistic, and we could use them in a downstream task. And for example, I will just show you a simple one. We did like facial expression recognition because our medical partners are interested in this, because often patients cannot really do certain expressions well, simple as smiling. So, for example, we see that when we use the residual masking net for like expression recognition, that we get predictions all over the place. And in this case, for the reconstructed face, we get like these distinctive spikes we have in our data set. So everything works there well. On the other side, let's take a look at like this EMG-based synthesis. Here we have like the simple task of void wrangling. And the input for this video is just the EMG data. And on the right, you can see the reconstruction we have by the parametric flame model. We also trained, or like we also tested way more existing monocular 3D reconstruction methods based on the reconstructed methods and the occluded images to check whether it works or not. And we also have like, which is interestingly, the surprise movement, which is basically this muscle here, which has the interesting property that is a digestive muscle. So the actual activation is when you chew. So you only have a certain spike to relax the muscle to actually move your jaw down. And this is really complicated in the EMG data, but we are still able to recover this certain moment. Then what we also have like is the camera-based muscle analysis. We train this whole model like on static images, but we're still able to recover certain dynamic properties of the signal. In blue here, you can see the original muscle activity envelope recorded. And in red and green, you can see like the prediction. And we see that we have like sometimes small spikes. We underestimate the true original signal, but the overall shape is good. But we also observe like an electromechanical delay, as our medical partners explain it. So the muscle fires earlier because it has some inertia to actually activate a move, and this movement is later visible in the video. And our model cannot handle this because it's just trained on static images. So in the end, our proposed method, EIFER, can reconstruct, or it's like a new form of like more occlusion-robust monocular 3D reconstruction, and we train it like in a cyclic structural manner. For the training, we only needed unpaired references, and we did a lot of experiments like how much data actually do we need, which kind of movements do we need, and you can find all this information in the actual paper. The preprint is already available. And right now we solve 3 tasks: appearance reconstruction under this occlusion, expression synthesis, and muscle activity analysis. And I already talked a bit about it, but like this whole data set, mimics and muscle, will be available, or at least certain parts of it. And we have like multi-channel SEMG data with 2 different kind of like electrode schemes, quite typically used in the medical domain. And we just have a monocular video recorded with the inter-resonance camera. It is rich in variety, at least for this kind of medical standard data sets. In the private one, we have like 36 probands without neurological disorders, including me. I'm the +1. My data will be completely available without any restrictions. And in the public data set, 20 of the people actually agreed to be released. We test like functional movements where only one kind of muscle is supposed to be working, and complex dynamics. And we repeated the whole recording setup twice with 2 weeks apart to whether see like if there are individual changes between the weeks or like if there's a daily offset. And it's the first dataset of its kind, will be public soon, and there are many tasks which I, as a single PhD student, cannot solve completely alone. And here you can find the project page. If you have more questions, I will be here in the poster session, and you can always write me in the contact information I have there. And with that, I would be at the end, and I would like to answer any question you have.
If you have any questions, like feel free to ask. I just go out with the mic. It's all right.
So you found better accuracy with the cycle gun. Very nice talk. You found better accuracy with the cycle gun unpaired training instead of like having the person do the same expression while wearing the electrodes versus not wearing the electrodes, because that would have like created a one-to-one mapping between the two things that you're trying to solve, right?
The thing is, like, our people are instructed to follow like an instruction video takes 20 minutes. The whole setup in total for a single person is around 2 to 3 hours, because the application of the electrodes takes a lot of time. And we found this way more intuitive, because these people repeat the functional movement, for example, 3 times. 1 time short, 1 time medium time, 1 time long time. And there's no perfect timing cue when they start to do that. Mm-hmm. So this way we can be 100% sure that what we actually see in the video, in the reconstruction, is actually the synchronized with the EMG data, just to be 100% sure.
Right.
Possibly a stupid question. Why not stick some green dots on your EMG sensors and use landmarks?
We also tried it before. We had like a lot of the different kind of ideas to solve this. And in the end, we just moved to this fully data-driven way, because we did not want to have any assumptions.
Okay.
We also had like another recording where we had just dots and everything. We tested many different things, and this is what worked in the end best.
Okay.
Also from a time perspective.
Anyone else? Okay, no more questions. Thank you. So
You're welcome.
moving on to the next speaker.